Hello, my name is Carter Lance, and today I am going to talk about Cobalt, which is a constraint-based alignment tool for multiple protein sequences. This paper was written by J.S. Papadopoulos and was published in the Bioinformatics journal in the year 2007. So from the title of this paper, we can see that Cobalt aligns multiple protein sequences to determine their similarity. Cobalt is a constraint-based alignment tool, meaning that the user can input certain constraints on the data in order to provide more accurate results. Conserved domain and motif databases are used as constraints for the sequences. The accuracy is comparable to similar databases, as we'll see in the results, and this tool is also faster than comparable databases. This is the abstract for the paper. It shows the motivation, results, and availability of this product. I included this slide just in case somebody wanted the overview of what was going on in this paper. Many tools aim to simultaneously align multiple protein sequences. Some of these tools detect conserved motif and domains inside each of these sequences. Common alignment techniques such as cluster W and muscle employ progressive alignment techniques. Cobalt will look at three things. It'll use databases to improve the quality of results, these being the conserved motif and domain databases. It will use local pairwise similarity to compare sequences and will allow the user to specify constraints. Penn and Blossom use scoring matrices based on the log-odds score. These two tools are useful when comparing few sequences, but not really when comparing a lot of sequences. Cobalt uses a conserved domain database and ProSite to align sequences. RSP-BLAST is a tool that searches domains in CDD. ProSite pattern identifiers are much shorter, and in doing so, certain constraints need to be put on the sequence before ProSite can be useful. Multiple alignment benchmarks are set up for comparison in this experiment, and I will get to those a little bit later. Overall, they hope to find that Cobalt can perform up to the standard of the benchmarks. So there are 6 steps that they used in order to align sequences. Number 1 was to find alignments for generating constraints. So they used RSP-BLAST to find conserved domains, they used BLAST-P to find local alignments, and PHI-BLAST in order to find protein motifs. The second step, after generating constraints, was to find partial profiles for each of the sequences. A subset of this was finding a frequency of similarity, that's what they called it. The frequency of similarity determines how close the sequences are to each other. After they found how close the sequences are to each other, they generated a guide tree. The formula for the distance is shown below. This equation shows distance between a certain sequence I and a certain sequence J. And from these, they calculated a guide tree. After they generated a guide tree, they used a Needleman-Wunsch method to compute global alignments, and this is their formula with all the constraints they had on it. After this, they created bipartitions and realigned. This accounted for any error in roots of the tree. What they did was they separated the alignment into 2 sequences and performed a profile alignment. The 6th step is to refine when new constraints are found. So you can put in more constraints when conserved domains are found or motifs are found, and this should increase the accuracy of the results. Cobalt was developed with C++, and it was built with Base 2.0. The benchmarks used to compare the multiple sequence alignment tools are Base 3.0, Homestrad, IronBase, Prefab 4.0, and SabMark. The scoring alignment that was used to compare the different multiple sequence alignment tools is given by this equation here. The equation encapsulates all the variables that they could encapsulate with this formula. So these are the results of the experiment. As we can see, there are numbers on the screen, and these are the Q-scores for their experiment. The Q-scores represents how well each of the multiple sequence alignment tools find core regions. Cobalt keeps up with ProbCons and PMCA. Those are the two most accurate multiple sequence alignment tools, and it does a lot better than Muscle and W in most situations. If you look over, there's the running time. The running time for ProbCons and PMCA are pretty long compared to Cobalt. So Cobalt has a much shorter runtime than that. It has a longer runtime than Muscle and Clustal W, but we see that Cobalt is more accurate. So we can see that Cobalt is a good balance between speed as well as accuracy of results. The paper realizes that the Q-score hides the fact that there could be variation between different samples. The table down below shows the variation of certain tools on alignment quality with the Q-score. And we see that in a lot of benchmarks here, there's a lot of variation, and the paper realizes that. But they conclude that Cobalt provides a good balance between runtime and quality alignments. So when we look at all the results, Cobalt is shown to be good at transforming pairwise constraints into multiple sequence alignments. User input that Cobalt provides maximizes the efficiency of the alignment. Cobalt provides several heuristics for aligning sequence profiles. In the future, they'd like to find computationally inexpensive motif finding tools in order to increase the accuracy of the tool as well as the speed. They are also going to look for ways to improve performance when sequences are divergent. It's hard to align sequences when they're divergent, so they hope to find ways to improve that performance. And they're also looking for ways to improve performance when similarity is high. When similarity is high, they may not need to go through all the steps in their algorithm, and therefore they can bypass some steps when similarity is high, and they're looking into that. So in conclusion, Cobalt is a multiple sequence alignment tool for protein sequences. Motifs and local alignments are looked for in the sequences with CDD or ProSite. The constraints can also be user-defined in Cobalt. The accuracy and speed of Cobalt are comparable to that of other multiple sequence alignment tools, such as Clustal W or PMCA. In the future, Cobalt will have better motif finding tools in order to make the tool more efficient. Cobalt will also become more efficient with highly divergent sequences, as sometimes it's hard to align divergent sequences. And in the future, Cobalt will become more efficient when similarity is high. When similarity is high, you don't need as many constraints on the sequences, and it can become more efficient if you do not have those. This concludes our presentation. Thank you very much for listening.